Hi class, and welcome to the solution video for parallelogram of forces. So we'll start with bronze and we'll work through to gold. So if you did the gold task, clearly you can fast forward to that. Otherwise, we can start our journey now. Alright, so let's look at the bronze task. So use the parallelogram rule to carefully construct the resultants. And you can see here they've given us a scale that 1 centimeter is equal to 1 Newton. So let's start by drawing in our parallelogram. So very similar to what we were doing for what I showed you for the scale drawing tutorial video. So with this one, it's going to be a little bit nicer, and in fact, actually, in order to draw the parallelogram, I'm going to use my protractor because I can see through it, and it does show me lines that I can line up to make sure, so I don't have to do, I don't have to actually use the protractor to find out angles. I know that these are all right angle triangles, or they will make rectangles. So what I'm going to do is I'm actually just going to use that horizontal line here, that line there, to ensure, I'm going to use it like a set square. So I know that this line here is perpendicular to that line. So I can just draw in my parallelogram using my protractor. Again, if you have a ruler at home, you can set it up so that hopefully, again, the thickness of the ruler as well. Again, you assume the lines are, but you can see my ruler is a bit too thick for this. So you are more than welcome to just use your ruler as well. But we have to just make do, don't we? This is going to make us strong and adaptable and resilient. So I'm going to hold my pencil here, and I'm going to then line up my protractor, and I'm going to actually just draw kind of a dotted line here. So again, just like in the tutorial video, what I'm effectively doing is I know that that vector is going to lie along that line there. So, again, I've not measured it yet, and I actually technically don't need to measure it if I can make sure that that line is really perfectly perpendicular. Now I'm going to do the same thing over here. I'm going to put my pencil at the top, and I'm going to line up my little set square here. And actually, you might even have a set square in your little your bag of utilities, resources. Okay, so now where those two meet, and I wasn't there, right there, I know is going to be where my vector intersects. It's going to go from the tail of the first one. So again, what I've done here is I say, well, I can move that vector here. So that's that vector moved over there, and this vector moved up here. So again, in both scenarios, I have that one has moved up, tip to tail, and then that one has moved over here, tip to tail. So no matter which one we choose to move, it doesn't matter. It's still going to give us the correct answer. I usually only do one because you can see by me putting in that second one, it's kind of ugly, isn't it? So it's kind of hard for me to see, but I know right there is going to be the tip of my resultant. So I'm going to go from the tail of the first one, and I'm going to draw a line all the way over to the tip of that one. And there's my resultant. Easy peasy lemon squeezy. So I'm going to again draw my arrow because it's a vector. We're looking at forces, and forces are a vector. And now all I need to do is I need to measure that guy. So I'm going to go from the tip there, and ooh, that's almost exactly, look at that. Almost exactly, I think that is 4 centimeters, and 1 centimeter is 1 Newton. So that is going to be 4 newtons. And again, let's make sure we have the direction because vectors have direction, and that is going to be 4 newtons. And that's going to be, again, what you could have done here if your protractor doesn't go there, is extend that line a little bit to make sure that it's nice and neat and tidy. So I'm going to just do a little light line like that, just to make sure that I can get an accurate reading on my protractor. So like there. So now oh, sorry, I'm totally off the page. There was a miss. That's off the page there. So I can see, oh, I'm going to flip this around too, because it's easier for me to read. I don't have to worry about doing mathematical calculations in my head and make a fool of myself in front of my students. So the 10, 20, 30, 1, 2, 3, 4. So 34. So that's going to be 34 degrees. Excellent. So we totally nailed that first one. So we can do the next one really quite easily, can't we? Because we know how to do this now. So again, do the exact same thing. I'm going to line up my protractor. I'm going to put my little pencil here, and I'm going to make sure that that's nice and parallel with my vector there. And I'm going to set my line straight up and go bloop, So there's my one side. So again, that's going to be that vector moved over here. And I know how high that vector is because I'm going to bring this one over as well. Again, I'm going to put my pencil right there. I'm going to line that up with my vector. And I'm going to go, bam. So there's my parallelogram. And I know that from the tail of the first one, again, if that's my vector that I've moved over there, to the tip of my last one, I'm going to draw in my resultant. So from there and all the way up, bam, there's my resultant. I'm going to draw my arrowhead on it because you always have to draw your arrowhead because it's a vector and vectors have magnitude and direction. So now I'm going to measure that guy. And again, I'm going to take my ruler, I'm going to line it right up to the tip there and then to the base, and that is 4.6, I would say. Again, you'll always be allowed a leniency of at least 1 millimeter. Yeah, I'm going to say that's 4.6. So that is 4.6 centimeters and therefore 4.6 newtons. And I'm going to also measure the angle because vectors have magnitude and direction, and that looks like that. Again, I don't trust that arrowhead there because I don't think it's clean enough. I'm just going to do a quick little extension of that line to be able to really make sure that I know my angle, and that is going to be at 64 degrees from the horizontal. Lovely. All right. Ooh, this one's a little bit different. We're not scared though, because again, just like we knew when we talked about that one of those first problems we did in the first tutorial, if I'm being pulled that way and pushed that way, I know I'm going to be accelerating up that direction. If I'm being pushed that way and pulled that way, I know I'm going to be accelerating in that direction. So just to make sure that we know which direction we are going to put our arrowhead, always trust your gut in physics. That's a nice thing about physics, is that it is based in our reality. So we can always trust our instincts as well. So I'm going to line that up nice and draw my line over. I'm going to do the exact same thing down here. It's a little bit more awkward. For those of you who are left-handed, this will probably be easier for you. All right, and I'm going to line that one there. Oops, I need to bring it in a little bit because I can tell the thickness of my pencil is actually going to make that line not perfect. So there's my parallelogram. I'm going to go from the tail of the first one. Again, imagine I've moved that vector over to there, tip to tail, tip to tail. I'm going to put my pencil there. I'm going to rotate that around, and I'm going to draw in my resultant vector. So I know that whatever thing is being pushed in this direction. I'm going to draw my arrowhead on there because I know force is a vector, and vector has magnitude and direction. Now I need to measure it. So I'm going to measure it up, and that's going to be, that's exactly 4.62. So that's going to be 4.6. I wonder if, again, I'm just turning a little bit there so I can write properly. Let's find out if the angle's the same as well. It looks a little bit longer. Again, I'm going to extend that up a little bit because I don't trust my arrowhead is obscuring my angle. So let's find out. Again, I'm making sure that the nice lined up there. I'm twisting this a little bit to make sure that it is parallel with the other line, and that goes up to 40. So up there again, I'm going increasing this way. 47. So 45, 46, 47. So not quite as steep. 47 degrees from the horizontal. And last but not least, again, nice right angle parallelogram. I'm going to, oh gosh, there we go. I'm going to turn that, I'm going to get that lined up there. I'm running that line nice and parallel with my horizontal vector here. I'm going to make sure that my pencil width is not going to make me go further out than I need to. And bam. I'm going to go, oops, oh, that's really, really gross, Mrs. Aikens. Let me tidy that up a little bit. And then I'm going to do the same thing here. I'm going to, again, put my pencil there, so I'm compensating for its thickness, and then I'm going to draw my line over. So again, that it would be this vector moved over, bam, there, going tip to tail, and then again that's going to be that vector moved up there tip to tail. I'm just going to write one and then there so I don't make it too sloppy. And I'm going to then move that around there. Again, that's going to be the thickness of my, bam, there's my resultant. I'm going to draw an arrowhead on it. Why? You all know now because it's a vector, and vectors have magnitude, size, and direction. So that's why I know it's going in that direction. Again, I'm using my gut to also tell me, well, I do know I've done it tip to tail, so I do know from the tail of the first one to the tip of the last one is going to give me the correct direction. But I always am going to check it with my gut as well. I know if I'm being pushed that way and pulled that way, I'm going to be going that direction. All right, so now let's find out what the magnitude is. I'm getting my ruler out. I'm going to place my tip there, and that's like 4.1, I would say. 4.1. So 4.1, and since it's 1 centimeter per newton, that's going to be 4.1 newtons. And last but not least, we're going to get the direction because vectors have magnitude and direction. I'm going to just say that so many times you guys are going to like never ever ever forget, but then you'll probably also be like having me like pop up into your head, like one of those like really annoying commercials that get stuck in your head. It'll be like Mrs. Aiken saying, vectors have magnitude and direction. I'm not cracking up, guys, I swear. I'm doing amazingly good considering. And there we have it. Like, yeah, right, you're right. Now again, that one there is making this a little bit tricksy for me, but I can see that is 39 degrees. Let me check again, actually, because I feel like I've just been like talking to myself, thinking I'm talking to you. And yeah, that's right before 40. So that is 39 degrees from the horizontal. Gosh, I'm feeling pretty proud of myself, guys. Hopefully you're doing this with me, and you can see how really kind of cool looking that is. It's like an art piece. All right, fantastic. So we have found out the resultant forces for each one of our vectors. Now let's do one where we don't have a picture. So a bike is being pushed. The magnitude of the force pushing the bike forward is equal to 87 newtons. A resistive force with a magnitude of 24 newtons is acting in the opposite direction. Find the magnitude and the direction of the resultant force. So this is actually not as complicated as a problem. I mean, there's lots of words and stuff, but what it's saying is that we have 87 newtons force going in that direction. And then we have, thinking about like a little free body diagram here, we have 24. Again, I'm not going to do scale drawing for this one because actually we can do this without a scale drawing. So if I'm being pushed in that direction, there's a resistive force of 24 in that direction. We need to just calculate the resultant horizontally is going to be 87 minus 24. So 87 minus 24. Again, if you have really good mental maths, you can do that in your head. Oh, my thingy's gone crazy there. But again, you can always have a calculator in physics. 87 minus 24 is 63. So I would use it. Hey guys. I would use it, a calculator, because then you don't make any silly mistakes. I mean, you can plug it in wrong to your calculator, but it's not typically likely because you can just check it. All right, I'm not done yet though, am I? Because that's 63 newtons. And again, because it has direction, we want to make sure that we make that very clear. So we know that 87 is dominating this scene. So just kind of think about it as tug of war here. So we know it's going to be 83, again, to the right. And that lets the examiner know that we know the vectors have magnitude and direction, and that it is to the right. We can do our quick little calculations there. All right, guys. Well, that is the bronze task nailed. So let's move on to the silver and see how that one can work. Now, this one is going to be a little bit trickier. We have a scale, which is not a one-to-one scale, and we have vector diagrams, which are actually not at right angles. So we are going to have to be a little bit more careful about this one. Now, let's see if I can actually, what I can do here, if I don't want to completely measure it out like I did the scale diagram when I was trying to be really, really careful, I can actually, with my ruler, just put in kind of like a little dummy line there, and that dummy line tells me, well, I know that vector is at that angle. So I know that's going to be parallel. So and what that allows me to do is that allows me to not have to kind of measure out all of the angles. You can absolutely 100% do that, but I don't want to actually bore you. I see that this is already up to 15 minutes now, so I'm going to try to keep on moving right along. So I'm going to use that as a guide, as making sure that my ruler now is parallel to that, and I'm going to just draw a line from the tip of that vector up. You can see that that is pretty darn close. And again, whenever we're doing a scale diagram, they're always going to allow us to have a little bit of uncertainty. I'm actually, now that I'm looking at it again, I'm not terribly happy with that because I can see that it's not quite to the tip there. So I'm going to make sure, again, I want to use this guy because this one doesn't rock. I'm going to hold that there. I'm going to line that nice up. Ooh, and my shadow is actually quite nice because it shows my shadow parallel with there as well. Okay, so there's going to be that vector. So that's that vector moved over to that point. And then I'm going to, this one's a little bit easier because it's parallel. So I'm going to come up here. Actually, I don't trust that either. I want to make sure that's a little bit clearer of where that is because, oh gosh. Oh, I need to go let my chickens out, but hold on, I'll finish this first. Daniel? Can you let the chickens out, please? I'm going to draw that line. Again, I'm making sure that it's nice and parallel there. And there's my parallelogram. So I'm just going to erase these lines here, just to make sure that I'm really clear about where my parallelogram is. And you can see here, there it is, has nicely emerged there. So I now know, again, this is where it gets a little bit tricksy, and you want to make sure that you use your arrows of one of your vectors. Again, I've moved that vector over here, so there's my tip to tail vector there. And I am now going to, it looks a little bit unparalleled there, but I'm not going to be too picky right now. Again, if this were exam day, I'd be really, really clear. Right now, I want to make sure that you know how to do this. Again, from the tail of the first one to the tip of the last one. And this is where it's a little bit harder to see, and that's actually the diagonal there. So there's my resultant. Bam. And now I need to measure it. So again, going from the tail of the first one, if I move that vector over there, or if I move that vector up there, it's still going to be the tail from the first one to the tip of the last one. And I'm going to now measure that up. And that's going to be 3.9. And again, 1 centimeter is equal to 10 newtons. So 3.9 centimeters is equal to 39 newtons. And I'm going to now measure my angle as well. And that's going to be, oh gosh, that is like dead on 50. Nice. I don't have to draw my little line up. That's 50 degrees. Lovely. All right, let's do this again. See, my focus isn't working here. Again, see if I can get my line here. Again, why it's really nice to have a clear ruler, because I could just line that up there, but I can't see it very well. So I'm just going to draw my other line in there. Bam. And I'm going to use that as a guide here. And I'm going to draw my parallelogram here. Again, trying to make sure that that's nice and lined up. I might actually want to stop being so lazy and actually measure the angle. But I'm not gonna. I'm gonna be strong in my laziness right now. All right, so I know this one again. I've drawn that parallel line there, so that's again moving that vector over here, and I'm going to now line that up nice and parallel, and from that tip there over. Yeah, I'm happy with that. So again, that's going to be that vector moved over here. There's that tip to tail there. So I'm going to go from the tail of the first one, and notice I'm kind of a little crooked there, to the tip of the last one. I'm going to connect those babies up. I'm going to put my pencil there to make sure that it is nice and accommodating for the thickness of my pencil. And I'm going to make sure that that one is as well. And I'm going to draw a nice line in. And there's my resultant. Again, I'm going to put my arrowhead on it to to make sure that I represent the direction of my vector, and then I'm going to measure it up. So let's see what that is going to be. That is going to be 6. So that's 6 centimeters. And again, I remember that 1 centimeter is equal to 10 newtons. So that's going to be 60 newtons. And again, I'm going to measure my angle. And my angle is going to be 32. So again, I didn't flip this time, but that's okay because I can see this 10, 20, 30, and then there's my 30 line there, 1, 2. So that's going to be 32 degrees from the horizontal. All right, let's keep going. I'm going to erase those little lines there to make sure that they don't confuse me with the next one. And I'm going to line that one up. So again, let's do that line there. So I'm going to again make sure that that's nice and lined up there. I'm going to actually have to stand up and get over the top of it there. And that's going to be my line there. And I'm going to now draw my line in there. That's actually quite a far away as well, but I can still tell that that's about parallel there. And again, I'm going to do the same thing here. That's actually not particularly awesome, is it? Something like that. Oh, that doesn't really help me, does it? Too much. All right. Oh gosh, and I'm totally off screen now as well. So sorry, guys. I'm actually not confident that I can do that one correctly. So I'm going to use this, which is a bit clearer. And that's going to come, I'm actually going to line it up with the next one over here, because I know those are all going to be parallel. Oopsies, that's what I wanted to do there. So what I'm doing here, because I didn't trust that way with my ruler, is I'm using the straight line of my other one here to move it across there. There we go. So now I have my parallelogram. I have a bunch of other lines here as well. But again, if I move that vector over here, and that's that vector there, so again, there's the arrowhead. So just so I make sure that I'm getting the direction of my vector correctly, because we have actually, two parallels here. So again, if I'm being pushed that direction and then pulled back, that's going to be the kind of magnitude that I'm going to move. So I'm going to take that and I'm going to connect it up there. Again, the tail of the first one to the tip of the last one. And there's my vector there. I'm going to put my arrowhead on it to complete it so that I know the direction that it's going. And now I'm going to measure that. And that is going to be, looks like exactly 2.6. So 2.6 centimeters is equal to 26 newtons. Again, the angle here is going to be a little bit more, I guess, difficult. It's not because it's going downward now, but you can still say from the horizontal and from the vertical. So I'm going to use the horizontal line here, and I'm going to line that up. And you can see here, it looks like it is just shy of 60, so 59 degrees. And last but not least, I've done all these tasks, so I'm getting a little bit tired now. So let's do this one. And I'm going to make sure that that's lined up. Oh, this is not going to be very good. I do need a new ruler. Let's see if that's going to work though for me. It will be good enough. So I just made that parallel line, so I have a reference here for it. And again, that's going to be my vector moved over here, and then this vector being moved up here, again making sure that I have the reference there for it, and that is going to be boop, 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 right there. So there's my parallelogram. Again, I'm going to erase these reference lines because it's going to throw me off, isn't it? So there's my reference lines erased. And so that would be effectively this vector moved up here. So again, going tip to tail here, and I've moved that up there. There's that vector there. Bam. So if I move that vector up there, moving it from tip to tail, I'm going to now connect those babies up. Again, I'm going to go from the tail of the first one to the tip of the last one. and that's going to be the journey I take. So again, I'm moving up that vector, and then that vector has come back, so my resultant is connecting that tip to tail. So that's the direction of my resultant, and now I'm going to measure it, and I'm going to be able to determine what my resultant is. So that is 2.567. So that's 2.7 centimeters, which is equal to 27 newtons. And golly, that looks like it is practically dead horizontal, isn't it? So I'm going to put it in reference from the first one. So because, again, I'm not too sure what kind of context they're giving here. So that looks almost exactly 50 degrees. So 50 degrees from the first, from that vector. All right. So there'll be more context on exam day. Alright guys, so the box is being dragged along a table. The direction of the force that is pulling the box is parallel to the surface of the table. Draw a free-body diagram to show all of the forces acting on the box. Okay, so here, let's put ourselves in the position of this box here. So we have our box, and that's going to be my free body diagram. So there's going to be, there's my box, and it's sitting on a table. I don't care about the table because it's a free body diagram. So again, there's the center of mass. So as we learned in our last lesson, the center of mass is at the center of a uniform object. So again, if this is a box, we're making the assumption that if it's on a table, it's on Earth. So it's going to have weights. The first thing I always think about is the weight that is acting downward. Now, if I have a weight and it's sitting on a table, that table is also offering an equal and opposite force upward. We call the normal force or the reaction force. Both are fine. Again, if this were an exam, I would really want to make sure that you are measuring those to make sure that N is equal to the weight. So they're going to be the same magnitude as well. So the box is being dragged along the table. The direction of the force that is pulling the box is parallel to the surface of the table. Okay, that's cool. Now, they've not given us a really important bit of information here. So if I'm being pulled parallel to the surface of the table, I'm going to be pulled in that direction. So that's going to be the, that's my pull. Now, the reason I don't actually realize now that I'm doing this question, assume there's no, okay, that's fine. You can assume there is no frictional force between the box and the table. So there's no frictional force, we just have the pull. So that means that this body is accelerating. It has a resultant force which is equal to the magnitude of the pull, and therefore it will accelerate. So actually, no, I am happy with this question. I'm so glad I didn't give you a bad question. Alright, so gold, use the Pythagorean theorem to find the resultant vector in the bronze task. So let's go back up to the bronze task. And in that case, we would have to know what the magnitude of each one of these is. Now, hopefully, I'm actually, guys, I'm going to pause right there because now I realize actually since these have been shrunk, it's not actually 1 centimeter, so it's going to actually give a different value to what is given here. So I'm actually going to pause that. And I'm going to probably cross that out until I can give you a, I'll say not to scale, actually. I'll say not to scale in that case. Yeah, let's do it. Let's do it. So if I know that in this case is going to be 3.3, so I'm going to say that's 3.3. And this one is going to be 2.3. So I'm just going to show you one of these, and I'm going to allow you to carry on with it because I realize this video is going way too long. Alright, so a squared plus b squared equals c squared. So that first one, again, it's not going to be to scale in this problem, but that's okay. I can at least still show you for the first one. So if I have my scale, which is going to be, I'm just going to redraw it down here really quickly. So that is 3.3. and that's 2.3, then I know that that is going to be, if I draw my little rough drawing of my parallelogram here, oh, that's a little bit cattywampus there. That's going to be my hypotenuse, and that's going to be the 2.3 over here. So it's going to be 2.3 squared plus 3.3 squared is equal to my resultant squared. So let's simplify that first. So we've written down our, well, actually didn't write down the equation. A squared plus B squared equals C squared. There's my equation. That's equal to my A, my B, and my C equals R, my resultant. So, so 2.3 squared plus 3.3 squared, that is equal to 16.18, oopsies, equals R squared. So R is equal to the square root of 16.18. So R is equal to the square root of the answer, which is 4. Oh, gosh. Oh, it is to scale. That's so awesome, guys. Here, I think I don't do this for a year, and I come back and it is, look, it is to scale. So let's erase that. Oh, I'm so excited. All right. I'm going to actually, though, what I'll do is, again, because I realize that this is going quite long, that's the first one. I'll allow you to carry on. I will scan these solutions so you can look at them and you don't have to listen to the whole 31-minute or more video. All right. So a boat is being pulled by 3 tugboats. The boat also experiences a frictional force from the water. These forces are shown to scale on the diagram. Using a scale diagram, work out whether the boat is in equilibrium. So what we're going to do here, I'm recording, please be quiet, is, I apologize for this because I realize that this is actually, there should be lines here, and it's really hard to see. So each one of these squares that's going to probably be a square there. Oh my gosh, this is so bad. Each one of these squares should be about, okay, good. They are 5 centimeters. So again, I can say 5 millimeters. So at least I can use that as a reference. So if that is going to be going up 1, 2, 3, that's going to be going up 3, isn't it? Yeah. Let me do it like that. There's 1 there, and 1 there, and 1 there, as we would expect, and 1 there. Okay, so that's gone up 1, 2, 3, 4. So that means that this one also is going to go up that many. So what I'm going to do is I'm going to start to construct a tip-to-tail vector diagram. So I'm going to start with moving this one over here. So I'm going to draw everything from this point here. So if that is up 4, there's going to be 1, 2, there's 1 there, and 1 there. So there's going to be, and it goes over 1. So I know that it's going to be up that direction. So I'm going to connect those up there. Let me actually make sure that that's really clearly the right place. So that's 1, 2, 3, 4, yeah? Nope, that goes 1, 2, 3. So it's going to go up that one. Let me make sure that that's also good there. 1, 2, 3. This is really annoying. Apologies, guys. I'm going to go from that line. Maybe your printers are better than mine. Or maybe actually, before I put this on Show My Homework, I'll try to make this a little bit darker. Okay, so that's that vector. I'm just going to put a little extra because I've already moved that guy over. And now I'm going to move this guy over as well. So again, let's get an idea of how many squares he is away. That's going to be 1, 2, 3, 4, 5 squares away there. So, and he's going up 1 square. So I'm going to be from that point there, 5 squares over and 1 square up. So that's going to be 1, 2, 3, 4, 5 squares over, and then that's going to be 1 square up. So that's going to be from this one that I can actually see. Bam. So there's going to be my next vector. Again, I'm going from the tip of that one, moving over to what would be that vector there. Bam. So that vector I've just moved here to there. So I'm going to cross that one out. And now, last but not least, I'm going to move this one over. So that one is 1, 2, 3 that I can actually see there, and then 1, 2, 3. So it's 3 over and 3 down. So again, 1, 2, 3 over, and then it's going to be 3 down. 1, 2, 3. So it's going to intersect right there, right along itself. Bam. So there's going to be my vector diagram. So again, I'm going from, so 1, 2, 3, 4, and that one's taken care of as well. So now if I'm going from the tip of the first one to the, the tail of the first one to the tip of the first one, it's actually going to be that vector there, which is going to be our resultant. And we can see there, that it is going to be 2 down and 2 over. So that's going to be a 2 and a 2. So 2 squared plus 2 squared and the square root of the answer. 2 squared plus 2 squared and the square root of the answer is going to be 2.8. All right. Sorry guys, I'm a bit exhausted now. But that last one was a little bit awkward. But I will go through and try to make it a little bit tidier for you guys before your lesson. All right, you guys have a lovely, lovely day.